Welcome to this explainer for completed lesson 4.4, where we're going to step into the shoes of a field biologist and learn how to solve the ultimate puzzle, identifying the unknown. Imagine you're out in the wilderness, completely surrounded by life, and you spot something totally unfamiliar. How on earth do you figure out what it is? Well, today, we're going to learn the actual secret code biologists use to unlock the natural world. Here's a quick look at our agenda for today. We're going to cover the identification problem, meet the dichotomous key, solving visual branching keys, decoding paired statement keys, and finally, putting keys to the test. Let's jump right in.
Starting with Section 1, the identification problem. I want you to imagine a super common scenario. It's a situation that absolutely every biologist, from eager students to seasoned professionals, eventually faces out in the wild.
What would your very first instinct be if you found a weird, many-legged critter you'd never seen before and just couldn't name? You might try flipping through pictures in a heavy reference book or endlessly scrolling through images on the internet. But as any seasoned scientist will tell you, simply comparing pictures doesn't always work out.
And looking at all this brilliantly illustrates why just guessing is basically impossible. Look at this massive, dazzling array of insects. We've got beetles of literally every shape, size, and color. Some are iridescent green, some are covered in spots, others have these incredibly long antennae. When you're confronted with this sheer volume of biodiversity, flipping through random pictures is like looking for a needle in a haystack. We absolutely need a highly systematic way to narrow down our options. To solve this exact problem, biologists use a highly structured investigative tool. And that brings us to Section 2, meet the dichotomous key. Biologists use what's called a key to help them identify organisms. A key is essentially just a set of questions about whatever it is you want to identify. Now, the absolutely crucial point here is that strange word, dichotomous. It strictly means branching into two. This forces us to make really simple yes or no choices, an A or B pathway, that slowly cracks the case by splitting our possibilities in half over and over again. Think of these 3 steps as the golden rules of the game. First, you must pick just one specific organism to focus on. You can't evaluate a whole group all at once. Second, you always start at the very top of the key. No skipping ahead or you'll get totally lost. And third, you simply answer yes or no, following the line to the next question. You just keep going until you finally arrive at the name of the organism. All right, Section 3, solving visual branching keys. Now that we know the rules of this biological detective game, let's see what this actually looks like in practice using a highly visual format. Notice how elegantly this visual setup separates vastly different creatures. We have a crab, an earthworm, a slug, a dragonfly, and a housefly. The key starts right at the top with one beautifully simple question. Does it have legs? Just by answering yes or no, we instantly separate the earthworm and slug from the crab and the insects. If we say yes, it branches again to ask, does it have more than 6 legs? It's just a brilliantly simple mechanism for sorting physical traits. Actually, try tracing it yourself right now. Let's look at the dragonfly. Start at the top. Does it have legs? Yes. Follow that branch down. Does it have more than 6 legs? No, it's an insect, so it has exactly 6. Follow the no branch. Does it have 4 wings? Yes. And boom, you've just positively identified a dragonfly using binary data sorting. How cool is that? Moving on to Section 4, decoding paired statement keys. Let's see how this visual logic builds into a slightly different, much more compact format that biologists frequently use when they're out in the field. Because as beautiful as those visual branching trees are, drawing all those lines and arrows takes up way too much space. In dense scientific reference books, space is definitely at a premium. So while visual maps use arrows to guide your eyes, text-based keys, which are also called paired statement keys, rely on a numbered choose-your-own-adventure system. Instead of arrows pointing where to go, a number explicitly tells you which pair of statements to read next. In this text version, you can see it's the exact same logic we just used. It starts with pair number 1. You choose between 1A, it has legs, or 1B, it does not have legs. If we're looking at our dragonfly and we choose 1A, it has legs, follow the dotted line across, the instruction explicitly tells us to go to 2. This drops us immediately into our next dichotomous choice about the number of legs. It is exactly the same tree, just written out as a list. And that brings us to Section 5, putting keys to the test. All right, you've got the theory down, you understand both the visual and the text formats, so now it's time to put your newfound detective skills to the ultimate test with some fresh, unidentified specimens. Imagine you're swimming over a vibrant coral reef, or maybe you're looking into a large aquarium, and you snap photos of these 4 incredible fish. They're labeled A, B, C, and D. And they look quite different from each other, right? Some have stripes, some have spikes. To figure out exactly what they are, we need to process them, strictly one at a time through our scientific key. Let's tackle fish D, the bright orange and white one. Step 1, does it have stripes? Yes, so statement 1A says go to 2. Down to step 2, are those stripes vertical or not vertical? Well, they run up and down, so they're vertical. Statement 2A says go to 3. Down to step 3, do the fins have spines? Looking closely at its smooth fins, no they do not. Statement 3B points us to our final answer, conclusively identifying our specimen as a clownfish. See? You're a natural. And this brilliantly illustrates that these keys aren't just limited to animals, insects, or fish. This final challenge shows we can use the exact same paired statement logic for botany. Look at these flowers. We can sort them by simply counting their petals. A key could start with 1A. The flower has exactly 4 petals, versus 1B, the flower has more than 4 petals. If it has exactly 4 petals, like flower D, the key immediately tells us it is Lunaria. The logic is totally universal. By mastering the dichotomous key, we see how breaking down the overwhelming diversity of nature into a series of simple A or B questions makes the entire natural world accessible to anyone. We don't have to be overwhelmed by a massive pile of unorganized photographs anymore. We just follow the clues, step by step, branch by branch. I really hope this explainer has given you the confidence to decode the natural world. Next time you explore the outdoors, how will you look at the unknown creatures around you differently, now that you know the biologist's secret code?